think so. Okay, so we're going to be looking at Module 1 tonight. You're going to be noticing this is going to be an introduction to kinematics. So we're going to be focusing on Chapter 1 in our textbook. And you'll notice here that in our learning plan, here's going to be the PowerPoint for Chapter 1. Now, as we go through each one of these modules, we are going to be covering 8 modules. Every one of these modules are going to be out of our textbook, so we're going to be covering a lot of material out of there. When I say read the chapter, okay, make sure that as you go through, if you end up reading ahead of time, always look at the PowerPoint, because although I say read the chapter, the only sections that you're responsible for are the ones that I'm going to be going over here in class, which are going to then be identified on the PowerPoint presentation. So there are usually sections that we don't go over because not everything is equally as important in each one of the chapters. So the PowerPoint is going to be our guide for what you're going to be responsible for. So we'll go back to that in just a minute. You're going to notice that there is a session recordings section here in the module. The session recordings that I do this evening will be populated here. So you'll notice that there is fall 2024 in there. That's obviously last year's recordings, which are identical to what we're doing this year as well. But I will populate with the new ones that we have tonight later this evening. And then you'll notice that we have our practice problems and our assignment. Let's briefly look here. On the practice problems, we will be completing these this evening through the work that we do in the lecture and the demonstration. Now, additionally, on each one of our practice problems, you'll notice that I have them highlighted here. There are 3 questions I always want you to answer, and you don't have to write an essay for each one of these, but I want you to really kind of be honest and think about these items. So the first one is, once we're done with our lecture this evening, I just want you to think of 2 things that you learned tonight. I'm hoping every week or every time we meet that I get you something that's new, but something that maybe was new or that you learned this evening, or maybe became more clear, after maybe taking some other courses that you've had. Then I also want you to tell me 2 things that you still feel like you need additional practice to feel confident on. Okay. And then lastly, it's always kind of fun to get your perspective on, after I've gone over the lecture, what do you think the main idea was? What do you think the main objective was? Not really going, I have them listed in the PowerPoint. Don't go back there. Just off of what we did. What do you think the main objective was? What was the point of what we did this evening? I always think it's good to get there, because that lets me know if what I'm going through is making sense and getting through to you guys as well. So those are going to be the practice problems that we do. We'll talk a little bit more about the instructions, but based on the stuff that we do this evening, you'll get a good idea, not only what to hand in for the practice problems, but how that's then going to translate into when you do your assignment as well. Okay. So those are the practice problems. I also want to briefly look at assignment number 1. It looks like a lot, okay? You'll notice that there are, if you count these all up, there are 12 problems, okay? They're broken into, I believe there's 6 problems here. So you're going to create kinematic diagrams for 6 problems from the end of the chapter, okay? And those are going to be worth 10 points each. Then the next 6 problems, notice that those are 5 points each. That's calculating mobility, but it corresponds to the diagrams above. So for instance, the mobility equation for 126 corresponds to kinematic diagram 1-1. So essentially, it's a 15-point problem where you're doing a diagram and a kinematic, or doing the mobility equations. So once we start going over things, this will make a little bit more sense. So I don't want you to freak out about the number of problems here. It does look extra a lot, but literally I believe it's 6 problems. And then we've got a couple case studies at the end that are short answer as well. So again, once we go through what we're going to be going through tonight, that'll make a little bit more sense and hopefully feels a little bit more doable than when you look at that long list. So let's go over to, I hope I started. Let's go over to our learning plan, and I'm going to pull up our PowerPoint presentation. And again, this is going to guide us through the chapter. For the most part, I have the illustrations copied in here, but we'll kind of go back and forth to the book as we need to. So chapter 1, the objectives here. So a couple of the things that we have listed here is, first of all, I want to get you used to the whole purpose and the need for kinematic analysis, okay? And as I had stated the last time we were together, kinematics ends up being the first step in the design process. It's kind of like the layout work that we end up doing, okay? Now, along the way, we're going to define components that comprise a mechanism. We're also going to be learning how to draw a kinematic diagram, as well as compute the number of degrees of freedom, or what we call the mobility, okay? I also want to kind of introduce you to identifying 4-bar mechanisms and also a slider crank mechanism, okay? So those are kind of the things that we're gonna be touching on. Now, as we look at our first section here, the introduction, this is where it identifies and defines what is kinematics. Kinematics is a study of motion without regard to forces, okay, that cause them or anything. So you're going to notice that the only thing we're going to focus on is going to be position, displacement, velocity, acceleration, but there is no force analysis here. So in kinematics, we are not worried about, deflections or stresses or what's the material or how thick that's going to be. Okay, that's statics and strength of material stuff. In kinematics, it's just the items we have here without regard to any forces at all. All right. Then when we look at kinematic analysis, as it says here, it's the first step in the design process. Okay, so it's layout work. That's really what we're looking at. And then the elements to answer some of those questions that we see above. Now, when we look at machines and mechanisms, a machine is going to be a device that is used to alter, transmit, and direct forces to accomplish a specific object, okay, or objective. So a chainsaw, for instance, it's a familiar machine that directs forces to the chain for the objective of cutting wood. All right, so that's a machine. That's a machine. Now, as we look at a mechanism is going to be the mechanical portion of the machine that has a function of transferring the motion and forces from the power source to the output. So in the case of our chainsaw, the power source is going to be the gas engine, okay? And then the output is going to be that chain that is going to do the cutting of the wood. And so there's kind of like an in-between there. There's going to be a mechanism in between to kind of go from that engine to the chain, okay? And that mechanism is going to be arranged with some rigid parts, and they're going to be connected, and they can be done in a variety of different ways. So we'll be kind of looking at different elements, not only for a chainsaw, but for other common machines that we come across, okay? Now, kinematic analysis is going to involve determining the following: what the position is. So as we look at a mechanism is going to be this connection of these rigid elements, okay? And they're going to move around, okay? So for instance, if we have this, I'm going to call it a crank, and that's what we're typically going to see it as. It can be considered the input. This crank is going to rotate around. It's connected to another rigid link that is connected to, we call it a slider or maybe a piston. And as it does that, typically we want to know, okay, as our crank rotates around, what is the displacement that is occurring on the output side of our mechanism, okay? In terms of position, where is it going to be positioned at any given moment? What is its displacement going to be? So if I go, for instance, 90 degrees of counterclockwise crank rotation, what does that do to the displacement of my slider on the other side, okay? How fast is something rotating? What is the linear speed or velocity of an element that is in our mechanism? And potentially, what is the acceleration as well? Okay. So it's the first steps. Notice again, there is no force here. There's no material. There's no thickness. We're not worried about what is the size of yet. Okay. We're just looking at those beginning elements of the design process. Okay. Now, for an example, this is figure 1-2. You're going to notice that is going to be on the top of page 2 in your book, and it's figure 1.2. And kinematic analysis, if we look at this platform that we see here, I think it's called an adjustable height platform. Some of the questions that kinematic analysis would answer would be, for instance, what is the significance of the length of the legs that support that platform? So if we look at how long these legs are, does that change the position of the platform on the top? Probably does, right? And depending on where you want that platform to end up, the length of those legs is going to be significant, right? Another question might be, is it necessary for the support legs to cross and be connected at mid-span? okay? Through kinematic analysis and moving things around, you'll be able to kind of, answer that question. Is there another configuration that we could go through? This is the beginning of the design process, okay? Another question might be, how far must the cylinder extend to raise the platform? Now, on this one, we don't see the cylinder in here, but if we go underneath the camera, the platform that I have here, I don't know why they're different. I got the illustration out of the book. There is a cylinder right here, okay? And that cylinder is what's going to actuate the platform. And basically the question here is, how far must that cylinder extend to raise the platform 8 inches, okay? So raising it 8 inches vertically, how far or how much stroke do we need on that cylinder to achieve that? Okay, so those are the types of questions that kinematic analysis would be interested in. Notice we're not dealing with force or what is the load carrying capabilities. We're only concerned with the required motion that's necessary to get the intended work done. Okay. Now let's talk about mechanism terminology. So this is section 1.4. This is on page 2 as well. So some of the terminology here, linkage. A linkage is going to be a mechanism where all of the parts are connected to form what we call a closed chain or a closed loop, okay? A frame member is going to be one of those links in the mechanism that doesn't move. It is always stationary. At times, we are going to be able to easily identify what is the frame on a mechanism. It might be bolted down, okay? So that's kind of obvious. It's not going to move. But other times, it might be an element that isn't necessarily bolted down. So for instance, I have a hand tool, okay, underneath here. So I've got a hand tool here. This is a vice grips, all right? Now, none of this is bolted down. I can pick this up and move it around. So when I look at a frame of the mechanism that moves here, okay, the elements that move relative to one another, what I need to do then is identify what the frame member is. So I would assign like the top portion right here is a non-moving element, and then I would move everything else relative to it. Does that make sense? Okay, so there's always going to be a frame. It might not always be secured down, but we need to identify the frame so that other elements are going to move relative to it, okay? So there's the frame. It's going to be the one link that does not move and is always stationary. Then the other links in this mechanism are going to be the individual rigid links that make up the mechanism to do the work that we want it to do. And then there's going to be joints. A joint is going to be a movable connection between two links and allows relative motion between those links. Now, the two main types of joints that we're going to be seeing are going to be pin joints and sliding joints. If we look at figure 1.4, not 1.3, 1.4 on page 3, okay, we're going to notice that we have an example of each one of these. On the left-hand side, this is a pin connection. So you're going to notice that we have a link coming in, link number 2 on the left, link number 1 on the right, and they are connected by a pin going through them. Now, because there's a pin going through, they now can rotate relative to one another about the center of that pin. Okay, so that's a pin joint, joins them together with a pin. The other type of joint that we see here is a sliding joint. So you'll notice that we have a block here, okay? They're calling that link 2. Link 1 is going to be basically the slot that this link is going to then move within. Notice that this slider is going to slide in a linear fashion. So in this case, it's a horizontal linear distance that this link is actually going to ride in the slot that we see here. So a pin is going to be rotational motion, one link relative to another, and a slider is going to be linear motion, one link relative to the other. Okay. Then there's different types of links. There's simple links and there's complex links. If we go on that same page, but we go past the cam and the gear, okay, we are going to look at down here the two different types of links that we have. The first link on the left-hand side, this is a simple link. A simple link is going to be a rigid link that has two connections on it, has two connections. So you'll notice here we have the link in the connecting the two pins that are then connecting to two other links. So pin and a pin on one rigid link. A complex link is when we have more than two connections on any given link. So in this case, we've kind of got a boomerang looking or a dog leg looking link, and we've got 1, 2, 3 pin connections on that one single link. And again, it can be more than that as well, greater than 2. So 2 is going to be a simple, and 3 or more is going to be complex. Now, just to kind of go back, we did skip the illustration here in the middle, which was the cam and the gear. And the reason we did is because these are considered what we call higher order joints. And we specifically revisit in detail cams, gears, and chain drives later in or towards the end. So the last couple of weeks of the term. So I kind of reserve these for then. So we're not going to talk about them right now. We're going to kind of keep it to kind of the basic stuff for the time being. And then we'll get more detail on those and deeper later on. Now, the last item we're going to talk about is going to be point of interest. And a point of interest is going to be an element that there might be a point on a link or on an element that we're interested in finding out what's going on. And these will become apparent as we start looking at mechanisms and drawing the kinematic diagram. So I'm just going to kind of leave it there. Okay, so we'll talk more about these as they come up. Now, kinematic diagrams. Kinematic diagrams are going to be stripped down or simplified versions of the machine assembly. Okay, so the purpose is going to be just to represent the variables that affect the function of that mechanism, okay? So for instance, we're kind of doing a backwards analysis here. Most often, as I said, kinematic analysis or kinematic layouts and diagrams are going to be the first step in the design process. We usually don't know what the final thing is going to look like, all right? We don't know all the details. So but what we're going to do here in Module 1 is you're going to be given a final mechanism or assembly, what it looks like, and you're going to go backwards and you're going to create the kinematic diagram for it because we got to start somewhere, right? We got to learn how to kind of equate these things. So we're starting here. So the kinematic diagram is going to be a very simplified version of the connections and such to the frame or to the items that don't move. And they're going to just represent overall what those elements look like and their sizes. So as we look from left to right here, this is a toggle clamp on the left-hand side. This handle is going to rotate up and down, or it's gonna oscillate, if you would, up and down. You would manually with your hand kind of pull this up and then push it back down. As you pull it up, the other side is going to come up along with it. It's going to, if you would, release the clamp. When we push it down, it's actually going to actuate the clamp so that it's going to hold something down, okay? So when it's in its down position, it will be nice and flat. When it's in its up position, both sides are up, okay? And so over on the right-hand side, we're going to use then standard symbols to represent what these would look like. So notice that over on the right-hand side, our kinematic diagram, the handle doesn't really look like the handle, okay? It's a representation in triangle form, but it's going to just represent the extent to which the motion or the size of that element or link is going to be, okay? So we'll get more into this, but over here is the final product on the left-hand side, kinematic diagram over on the right-hand side. So let's practice making a kinematic diagram, and we're going to go through this process in example 1.1. Example 1.1 is going to be found on page 6 in your textbook. So if you go underneath here, page 6 in your textbook, halfway down is example problem 1.1. Okay. Now, this is our first practice problem. So you are going to need to get out a piece of paper, and we're going to sketch the kinematic diagram for this particular problem, okay? And you will be handing this in. So as you are creating the sketch here, my expectation is that you're doing it in a way that is going to be readable and that I can see it, okay? Now, for this practice problem, I'm not going to open up the practice problems that we have, but in this case, this is going to be a sketch only. We're not doing this one on AutoCAD. We're just sketching this one out. Now, when we sketch it out, if you happen to have a straight edge, that's ideal. But if you just nicely sketch, that is going to be fine too. I'm going to be using a straight edge. So example 1.1, it says, figure 1.9, which is the illustration right down here, shows a shear that is used to cut and trim electronic circuit board laminates. Draw the kinematic diagram, okay? Now, as we look at this example, it gives us the steps for which we are going to use to create this diagram, but I also have them written on my PowerPoint presentation. So I'm going to go back briefly over here. And the 5 steps that we're going to go through are going to be number 1, we're going to determine what the frame is. So by looking at this diagram, we're going to talk it through. We're going to be identifying what the frame is. The frame is going to be the non-moving elements on our mechanism. Then the second thing is we're going to identify the type of each link or joint and we're going to use table 1.1, which is in our chapter here, to help us with that. Then we're going to draw each one of the links to scale. Now, in this case, you're going to notice that our illustration does not have any dimensions on it. So we are going to draw proportionally, okay, when we don't have dimensions. There will be, as we go along, in this particular module, module 1, we're just learning how to make the drawings. We're not going to worry so much about the dimensions at this point. But as we move into finding displacements and rotations and all that kind of stuff, then we are going to have dimensions. But for right now, we're just going to practice making the diagrams and learning the terminology and the symbology. Then number 4, it says you're going to number the links starting with number 1 as the frame. And then we're going to letter the joints starting with A as the frame as well. Okay. So here is our illustration, but I'm also going to kind of look underneath here because I can zoom into this one a little bit more. Now, as we look at our illustration of our shear here, okay, end up drawing in my booklet. The first thing we want to do, I like to, like it says, identify what the frame is. So when we look at this, and I know we can't move it around because we don't have it in front of us, but you'll notice that here we have a handle. So it's a manually actuated shear. And as you can see, this handle pivots around this point right here. Okay. This point is connected to this block that we can see has a bolt. All right. So this is a frame member, all right, because that is not going to move, all right. We can also see on the other side, we kind of have a mirror image of a similar piece. This is also a frame member. That's not going to move, all right. So our handle, I'm going to call this the handle. Our handle is connected to the frame at this point right here. That's where it pivots around. Now, as you can see, because it's pivoting around that point, I can actuate this handle, you know, if you would, clockwise or counterclockwise, right? Now, tell me, as I move this clockwise, okay, in this direction, this has what we call a connecting rod, okay, to that blade or that shear that is cutting off the electrical circuit board laminates, all right? Which direction, up or down, is this shear going to go when I go clockwise or actuate clockwise the handle? Dylan says up. Anybody else? So if I go in this direction, up or down is our slider or our everybody's going up, up, up. Okay. Yeah, you're correct. It is going to go up, right? So that means when I actuate it and I go in a clockwise or counterclockwise direction, it's going to go down. So this is manually going to be actuated, not around a full circle, but it's going to oscillate, if you would, clockwise, counterclockwise, clockwise, counterclockwise. And our blade is going to go up and down vertically. Now, in this case, that link, our handle, would be what we would call our input. Okay. It's where we're imparting motion to kind of like start the function of this mechanism. So our mechanism is going to have this frame connected to the frame, not moving, and a handle. Then connected to that handle as part of our mechanism, our next link is going to be this connecting rod, we'll call it, okay? Connecting rod, connector, something like that. And then the last link is going to be what actually does the output work for us, if you would. It's going to be that blade is going to cut through that circuit board laminate, okay? Now, as we look here, we are now going to represent each one of these elements. So frame. The frame is always going to be represented with, I'm going to draw it on the side here. It's going to be a half circle with two sides going down. And then it's going to like anchor, if you would, to material that's not going to move. And then right in the middle, we're going to have our connection to whatever link is going to be connected to it. Okay. So a half circle, straight lines down, and then anchored. We are going to be drawing this in CAD, but we're going to be sketching this in just a little bit. Okay. So that's going to be our representation of a frame. So we are not going to draw all of this material here on either side. All we are going to do where it connects to our handle, we're going to draw this symbol right here. That's what we're going to draw. Okay. So we are going to start by doing that. So I'm going to zoom out a little bit here. This is going to be my example 1.1. If you want to put page 6, that's fine. And the first thing I'm going to draw is going to be that. And again, I'm sketching best I can. I don't want to get out my here. Then I'm going to draw right in the middle here the connection point. So that's going to be my frame. And you can kind of see with that, especially with the hatching, if you would, or the slanted lines here, it looks like it's anchored, to something. It's not going to move. Now, attached to that, I need to represent my handle, okay? When I look at my handle, I've got to also know where are my pin connections. And the pin connections are going to be to the frame and also to that connecting rod. But then I've got this like extension here. Okay, I've got this extension here. So to represent my handle, okay, we're going to start at the center of our frame. I'm going to go right about there. This is going to be another pin connection. And then I'm going to continue to kind of extend it out. And then my handle is going to go back from the center of my frame connection. And then this is going to represent, if you would, kind of the thickness of that handle. Does that make sense? Now, again, we don't have dimensions here. We don't have angles. We're just going to proportionally try to, draw this, right? Probably could have drawn it at a little bit more of an angle, but that's okay. So what I have for my handle then, I have represented where it connects to the frame. And then I also have the pin connection to the connecting rod. And then this is kind of like the end of the handle. Now, something I want to let you in on is that notice that I only put closed in pins where there was pin connections. I did not put a pin on the end here because this is just the end of the handle. It's not connected to anything. Okay. So where I have a circle with a filled in, or if you would, a solid hatch, so we're going to use an AutoCAD, then that is going to be where I have a pin connection. Okay. So that's my handle. My next element is going to be this connecting rod going down to connect to my blade. So that is simply going to be a straight line. Okay. That is going to be a simple link. Okay. A simple link. Actually, both of them are simple links because they only have two connections to pins or pin connections on them. And then here it's going to be the pin connection here. Okay. So if I look back, each one of these, if I look back as identified, there's a table 1.1. It actually starts on page 5. Okay. And it shows us the kinematic representation for typical like elements that we're going to find on kinematic mechanisms. So the first one here is a simple link. So a simple link is going to be just a rigid link that has a pin connection on either end. Okay. And there's only two of them. Another simple link with, they're saying with a point of interest, but notice that it's just not straight from one element to the next. It's more like that handle look that we have. It's kind of got this, I'm going to keep saying it's a dog leg or a boomerang looking, but then it still has two pin connections, but there's a little bit of thickness there. That really is similar to our handle. So in both cases, we've got simple links because they have two pin connections on them. But this one has more that thickness, and this one is more that straight, simple one on each end. Okay. Then what we're going to do is we are going to represent our blade. Okay. And as we can see, when we oscillate our handle, our blade is going to go up and down. Okay. So when we show the blade going up and down vertically, in this case, this is linear motion. So that means that we are going to represent that as a sliding joint. Okay. A sliding joint is going to be a joint that is going to be represented by a rectangle. And then the direction or the placement of the frame that it's going to move relative to is either going to be horizontal, vertical, or at an angle if that's the case, but it's linear motion. So we are then going to, at the center of our pin connection here, we're going to draw our slider. It's going to look like that. Now our slider is moving vertically. So that means our, if you would, hatching or the frame that it's going to be constrained by is going to be in a vertical direction. This lets us know what direction the movement of that slider is going to be. So we vertically put the hatching. Okay. If it was horizontal, going back and forth, then we would put it horizontally. Okay. Now, whether you put it on the left or the right, you only put it on one side. You don't put it on both. Yes, as we look at this, this is by design. If we look at the details here, why isn't this zooming in? Zooming in. There is frame on either side, but we only show it on one side. Okay, that's the standard. Okay, so do not show it captured on this side as well, only on one side. And the side that you choose is going to be the one that makes the most sense for the rest of the elements that we have here. The right side, it would be kind of busy, you know, over here. So that's why I put it on the left. All right. So any questions so far about representing each one of those elements, the handle, the connecting rod, and the blade, as well as the frame? Okay. So now we have each one of our elements in place. We have our frame identified. We have each one of the elements identified. Now what we need to do is we need to number our links. Okay, number our links. The first link and number one link will always be the frame. The links are identified with a number and a circle around it. That's how they're identified, a number with a circle around it. Okay, and link number one is always the frame, always. Link number 2, 3, and 4 in this case, they don't necessarily go in any particular order, but we are going to see as we move along in the chapters here that typically the element that is attached to the frame, and it's our input, so our handle is going to be what we input our motion with. This is what we're going to call number 2. And it's number 2 with a circle around it to identify the link. Link number 3, we're going to call the connecting rod. So you put it by the connecting rod. And link number 4 is going to be our blade or our slider. Okay. So in this case, we have 4 links in our mechanism. We have the frame, which is a stationary link, the handle, the connecting rod, and the blade or the slider. Then we need to identify the joints. The joints are going to be identified by letters, no circles, okay? And typically, again, you kind of start with that input. So I'm going to do A, where the handle connects to the frame. B, where the handle connects to the connecting rod. C, I'm going to scooch it up here. That's going to be where the connecting rod connects to the slider. And then we have one more connection, and that's going to be the slider to the frame. So in this case, this is going to be D, okay?
Those letters never get circled.
They do not get circled. Nope, they stay just like that. Only the numbers get circled for the link designations. The letters do not get circles. And yeah, that's a rule. Yeah, I know. It's just what it is. Now, lastly, and they have this on their illustration, and then we consider points of interest, okay? When we look at this particular illustration, something we might be considered or be, interested in is how long that handle is and how much room it's going to, take up as it goes through its motion, making sure that we're not interfering with something or making sure that the travel of it isn't unreasonable for somebody to manually actuate it. Yes. Letter D is going to be, so the question is, letter D is going to be the letter representing the joint of the slider back to the frame. Okay, so a sliding joint is going to be D. Okay, C is the pin connection to the slider, right? Now, getting back to over here, point of interest. So if I look at the end of my handle, I might be interested in, all right, how much room do I need to make sure that this goes through so it doesn't interfere with something? Or I make sure that the actuation of it isn't unreasonable for somebody, to do, manually. Okay. So the end of that handle, we may see as a point of interest. A point of interest is going to be X, Y, Z, W. Those are going to be at the end of the alphabet. Joints are going to be at the beginning of the alphabet, beginning with A. Okay. Points of interest are going to be X, Y's, and Z's, right? Now, points of interest are going to be arbitrary based on the designer. Some of your problems are going to tell you to identify the end of the handle as a point of interest. Then you're going to add it in, okay? Others might not. So you don't have to put a point of interest on anything, okay? But you as a designer would have more insights on why you would look at something or not look at something, okay? So if you think, okay, they didn't say anything in the problem to put it at the end of the handle, but I think that's a good point of interest, then put an X, Y, or a Z there, okay? But if it doesn't ask for it, you don't have to worry about it. All right, so this is our kinematic diagram then that represents that shear in problem 1.1. Notice that we used kind of standard symbology for everything. And as we look at this representation, it doesn't look much like our final shear, okay? But that's okay. Remember, this is a stripped down, simplified version of what that mechanism is actually going to do, okay? So questions right now? All right. Then let's look at our next example. So I'm just going to verify that that's where we're going. I'm pretty sure we are. Yeah, we're going to look at example 1.2. Example 1.2 is found on page 7, about halfway down. And we are going to be looking at, the kinematic diagram here for a vice grips, okay? Now, you'll be able to see this a little bit closer. I'm not sure why I'm not able to. Did it freeze on me? No. I don't know. I don't know why it's not zooming in and out, but that's okay. So our vice grips here, we're going to have this top handle, bottom handle, connecting rod, and then there's like a jaw that is going to open and close. I happen to have one here in class. It's not the exact duplicate or the exact model here, but it's close as far as how it works. Now, in this case, the steps that we go through are going to be exactly the same. We're going to identify the frame, identify each one of the links, represent them in standard form, as well as the joints, okay? Now, as we look here, go back underneath here, and I look at my live and in-person vice grips, you're going to notice that, again, there is no bolting down. So I'm going to identify this top portion to be my frame. Now, although this is assembled so that this is a part that actually slips on the inside and they like crimp it together, this is all one, solid piece, if you would, even though it's made in two parts. Does that make sense to everybody? So when you look at the representation here, where it continues as a solid piece over the top, even though this technically is two pieces, it does act like all one piece at the top here. Now, attached to this right here, this pin attaches what would be the movable jaw. I'm going to call it the bottom movable jaw here. Okay. That movable jaw is going to be kind of like this triangle piece here. And then it is going to be connected to the handle. Okay. And the handle, if we keep the top in place, is going to actuate relative to the frame. Then the handle is going to be connected back to the frame one more time. We don't see the pin connection, but if we look underneath here, you'll see that it connects with a pin on the inside of that handle. So there would be a pin right here. So what we have is our frame. There are two connections to the frame. There's I'm going to call it the connecting rod here, to the handle, and then to the jaw. Okay. So let's go through the process of drawing the kinematic diagram for this. Okay. So starting with the frame members, there are two frame members right here, and they're about in line with one another. So when I look at this one, okay, this is going to be example 1.2. Okay. This is on page 7, right? And I'm going to start by drawing those two pin connections. Now, because all of the rest of my linkage is down below, I am going to draw my frame members so that they're kind of up here. Okay, does that make sense? That way, this hatching is not down below where I'm going to be drawing other elements. Okay, and they're pretty, use this, kind of make, they're pretty in line with one another. Okay, so those are my two connections to the frame. Do not connect these, okay? Don't connect these because there's not an element in between. They're just part of the frame. David, that's what you're gonna have. Nope, 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 nope. This is all a continuous piece, and this just means that these points aren't moving. That's it, all right? What I have seen students do, which I think is okay, if you're like, all right, that kind of bugs me. If you want to do something like this, that's okay. All right, but you are going to see it in the book, and the way I do it is just going to be, here are connections to the frame. All right, they don't move. Now, on here, the next element is going to be the two that are connecting here. Now, notice that there's a shape here. Simplified. All we're going to do is we're going to draw one line connecting this point from the frame to what's going to be the point on our handle. Okay, so it's going to be just a straight line right here. And that is that connecting rod, if you would. Okay. Now, when we look here, I just did this. This is the pin connection. I'm now going to draw my handle. These two are pretty straight to each other, if you would, or pretty horizontal. So I'm going to draw those 2 points about like that. And again, my circles filled in are representing the pin connections, not just endpoints, they're the pin connections. And then I'm going to show my handle going something like this. So it's probably could be more at an angle, but yeah, something like that. That's going to be my handle. And then the last piece I need to consider, going from this point on my handle, I'm going to go up to the frame and do a triangle to represent this moving jaw on the bottom. So I'm going to go up to the frame here. And then we're simply going to make this triangle. So this is going to represent kind of that front part where the teeth are, like this part right here. And that's it. Right. So those are my elements. Now I need to number my links and letter my joints. So I'm going to do my links first. Link number 1 is going to be the frame. We only show number 1 once, and we just put it by one of the frame members. So in this case, we've got 2 connections to the frame. Whether you put it on the right or the left does not matter, but you only put it once. Then whatever's connected to the frame, I'm going to call number 2. I'm going to start. I like to start where my input is. So for instance, I know that my handle is down here and it's not directly connected to my frame, but to get to the frame, the handle kind of goes through this part. So I'm going to start over here and consider that my input side. So I like to start my numbering there. If you do it on the right-hand side, totally fine. So if you called your triangle over here a number 2, I'll never mark that wrong. Then I'm going to call my handle number 3 and my jaw number 4. Okay. So I've got 4 links in my mechanism. Number 1 is the frame. Remember, it's a stationary link. 2, 3, and 4. 4 links. Then I'm going to letter my joints. Remember, the joints are always we start the lettering at the letter A. So again, I like to be on my input side. I consider this side over here as my input. I'm going to have A here, B, C, and then D. Notice there's nothing on the endpoints here. It's the pin connections. It's not the endpoints of links. Okay. If you letter them another way, but do not start in the middle of the alphabet. Don't start with M, N, O, and P. Okay. Start with A, B, C, D. Okay. And then in this case, makes sense that there would be 2 points of interest. One would be the endpoint of my handle. So I'm going to call that one X. And the reason I would want to do that, because then I would even maybe add a little bit more information. If I wanted to know how far open and how far closed this would be, to see if it makes sense, if you would, for like an average adult hand to actually operate this, right? Okay. Additionally, we would be interested in what's happening over here relative to the frame. Okay. So we'd want to know, like, when does it close? And how far do you have to go with that? And how far is it going to open so that I can, I can put it around something that I'm interested in. So I probably call this a Y. Okay. So there is my kinematic diagram. I have each one of my links represented in a standard format. I've got them all numbered appropriately, with number 1 always being the frame. Okay. Never call the frame number 2, 3, 4, 5. It's always number 1. Okay. And then all of my letters are going to be each one of my joints. Okay. Questions? All right. Okay. So that's kind of like an introduction to making the kinematic diagram. What I want to do is I want to now switch gears, and we're going to go to AutoCAD, and we're going to create what we call a start file that is going to have the elements of our frame members, our pin connections, a slider representation, and then also the labels that we're going to be using here. So I'm going to stop our recording here.